Okay, so last time we looked on a bit more complicated neural net, which is given by random features model, and we saw that there we are in need of calculating not just the eigenvalue distribution of an ordinary Wishart matrix, but we actually are faced with taking the product of Wishart matrices and then also apply non-linearities entry-wise. Okay, and that's what I want to talk a little bit more today and probably next time to show you what tools or how we address such situations. Okay, so this will be about this essentially non-linear random matrix model. Non-linear random matrix models. And in particular, I want to give you tools how we can detect this. And so in particular, I will give a new proof of Marchenko-Pastur, and then we will extend this to more general situations. So I mean, what we want to do is still looking on the resolvent, trying to get an equation for the resolvent. So it's a resolvent method, but we will somehow do it in a different way, and in particular, this way will allow us extensions, in particular by doing cumulant expansions. So cumulant expansions. Okay, so let me recall what we are looking at. So the neural network we want somehow to describe is that we have, of course, our input. So this is in R to the P, vectors in R to the P. And then we take essentially random features of them. This means we multiply them. So we go to a first layer in our network. And there we go to R to the M. And here the action between the input here and the output here is just a matrix W. So we have here just a matrix W, which we also will choose in a random way. Okay, and then in addition, we also apply the crucial thing for neural networks, namely a nonlinear mapping here. So here we also apply entry-wise a map, which I usually denote by sigma. So there we still go to R to the M, and then we want to understand somehow what we get here. So what we get here are somehow the features, the feature vector which we calculate out of the data which we has as an input. Okay, so if I have here a vector x, a p-dimensional vector, so let me write it as R to the P tensor 1. So this is mapped here on this side, of course, to, so I have my vector x, I apply the matrix W, so I apply a linear mapping, but then I also do entry-wise this sigma mapping. Yeah, okay, and then typically we are not only inputting one vector, but we do n independent copies of them, and I just gather those copies together in a matrix. And of course, the mapping here is in such a way that I'm doing exactly on this matrix the same as I'm doing on each vector. So I mean, instead of a little x, I'm putting in a capital X, which is a p times n matrix. So I have in n usually independent copies of my data vector x, and then this goes over to the same. I apply W to the matrix X, and then again I get out a matrix, and in this matrix I apply entry-wise this mapping sigma. Okay, and so this means this X, which is here the collection of my n data vectors, is mapped to a vector which let's say I call F. So maybe this here I call F. This is the feature matrix. Or if I do it for the for a data vector, then I get a little f, which is a feature vector. So the little f is of course a vector in R to the M. So it's in R to the M tensor 1, and if I do it here with the n copies with this matrix X, then I get out an m by n matrix. So this capital F here is an m times n matrix. And of course, in the same way as X is the collection column-wise of my data vectors, this F here is the matrix where I have column-wise the feature vectors here. So f1 is what I get from x1 under this mapping, f2 is what I get from x2, and so on, up to fn is what I'm getting from xn. Good, okay, so that's the setting which we want to understand. In particular, what do we want to understand? We want to understand in particular the distribution of the feature vectors which are coming out here. So I mean, usually we are putting in our x vectors which are given by a Gaussian distribution, and then we want to understand what do we get out here. So what we want is essentially the covariance estimator for this f. So in the same way as for x, we want 1 over n x transpose, the eigenvalue distribution of this. So now we want to understand the eigenvalue distribution of this feature vector, or of f times f transpose, maybe normalized in the right way. Because of course what we really want to see is somehow the asymptotics of this. Usually we can derive equations, precise statements in a limit if our sizes go to infinity, and as we have seen, the regime we really want is where all sizes go to infinity, but in a proportional way. And here actually we have now 3 sizes. So we have n, we have p, and we have m, and all of them should go to infinity such that the ratio between them remains fixed. Of course, m could be equal to p, but it doesn't have to be. I mean, I could embed the p-dimensional data into a bigger space. I could calculate more features. I could also calculate less. So this is somehow arbitrary, the relation between them. But asymptotically, I should keep the ratio fixed. So we want to understand the asymptotic regime so where all of them go to infinity. So p, n, and m are my 3 parameters. They go to infinity, but I want to keep the ratio fixed, and so I mean I could choose the ratio arbitrarily. So in principle I have 2 possibilities for numbers. So let's say m over n I want to keep fixed as gamma, or at least in limit it should be gamma, and let me also say p over m should be kept fixed. And this ratio could be a different ratio. So let me denote it by gamma twiddle. Good. Okay. So that's what we want to understand. Okay, and actually one can describe what we get there. And this is a theorem which I want, first to understand the statement, and then also try to give the main ideas of the proof. So that's the following theorem about this situation, that we really can, in this limit, describe the distribution of this. So this is a more general version, it's really a more complicated version than Marchenko-Pastur. So because it's not about one matrix, but it's a product of 2, and then the non-linearities. In particular, the non-linearities might be something which is nothing which usually you consider in a classical random matrix context. So that's maybe the most interesting thing. But even the product is something which we should see. Okay, and this theorem, I mean, such questions in different contexts have been considered, let's say, in the last 15 years, but in particular for this situation, and maybe also for the precise statement. This is by Pennington and Vora from 2017, and maybe more mathematically rigorous version is by Benigni and Péchet from 2019. Okay, but there are a couple of other people also working in this context. Good, but so what is this saying? So it's about this situation. So let me collect again. What are we talking about? We have our data matrix X. So this is a P times N matrix. And then we have this W, which are the weights in our neural net. So W, and this is a M times P matrix. So it maps a P vector, a P-dimensional vector into an M-dimensional vector. And both of them, I assume they should be standard Gaussian matrices. So this means all the entries are independent and all of them are Gaussian with mean 0 and variance 1. So both of them should be standard Gaussian random matrices. Okay. And then furthermore, I have the sigma. So the sigma, this is a function from R to R. This is something which I want to apply to the entries of my matrix. So sigma is a function from R to R, which of course should be sufficiently nice. Okay, so in particular, mathematically, it should be differentiable. In practice, maybe you want to apply the ReLU function, which is not differentiable. But okay, for proving something mathematically, I mean, you need some smoothness. And okay, then you can hope, maybe in the long run, you can even prove that you have the same properties for non-differential things. So we assume here it should be sufficiently nice function, and maybe I'm not really specifying this. So I mean, in particular, all derivatives have to exist. So maybe that's the main thing. So it really should be differentiable. So all derivatives have to exist. Which of course for the ReLU function is not the case. But nevertheless, I think one still thinks that things should also work then in this case. Okay, and then we want some normalization or some kind of centeredness condition on this sigma. So we center it somehow. I mean, so by shifting it, we can achieve this. So it should be centered with respect to the Gaussian distribution. So this means the following, that if I integrate it with the Gaussian density, then it should be equal to 0. So the integral over R of this function sigma of t integrated with respect to the Gaussian density, and let me normalize it, dt, this should be equal to 0. Of course, for this equal to 0, I don't have to normalize things, but maybe it's nicer to really integrate with respect to the probability density of the standard Gauss. Okay, so it should be centered with respect to this. And now, yeah, what do we want to consider? As before, we want to consider F. This should be now the matrix where I multiply W with X, and then I apply sigma entry-wise. Okay, but because I mean I have to go to the limit, I should normalize things in the right way. And this W should be normalized with somehow with the square root of P. So W is a M times P matrix. So I should, I mean, the entries have variance 1, but in a limit, I mean, in order to have a limit, the variance should scale with the size. So I actually should scale this with this thing here. Good. Okay. Yeah. And then, I mean, the X, I'm not normalizing it here, but in my feature matrix, I will actually consider, I will consider here 1 over n. That's the same way as we did it for the Wishart matrix. We looked on 1 over n x times x transpose. So the x was not normalized, but this 1 over n was actually doing the normalizing. But we put this at the end. So the x will essentially be normalized later. But the w, let me normalize it here. And then I get a matrix, and there I apply this sigma entry-wise. Good. Okay, so that's the feature matrix. And we want to look on this covariance estimator in a sense for this. Let me call this M. So M is just this 1 divided by M F transpose. And maybe let us also see what matrices we have here. So F is which matrix? F is a, we start at P and we end in M. So it's an M times P matrix as there. And then if I multiply F with F transpose, I get an M by M matrix. Okay, so this guy here is an M by M matrix. Good. Okay, and now, okay, so that's the setting. But now the statement is we are looking on the eigenvalue distribution of this in the limit. And so let me specify again the limit. Then in the limit P n M all going to infinity, but such that M divided by n goes to gamma and P divided by M goes to gamma twiddle. Then in this limit we have an eigenvalue distribution. And how do we describe eigenvalue distributions? Okay, maybe if you can write down explicit formula, that's nice. But in general, you cannot really write down explicit formulas for the density. For Marchenko-Pastur, we could it in the end. But I mean, how we proved it was that we looked on the Stieltjes transform and we derived an equation for the Stieltjes transform. And that's also what you can do here. You can derive an equation for the Stieltjes transform in the limit. And this equation can be written down explicitly. And in this case, it's a fourth order equation. So maybe you still can solve it, but probably you don't want to do it. Okay. So so in this limit, the Stieltjes transform, that's our favorite tool for dealing with distributions. So the Stieltjes transform of this M, this matrix M. So M is an orthogonal matrix. So it has a eigenvalue distribution on the reals. So this converges to a limit which I call S, and for which one can write down an equation. Okay, to a limit. So let me say S of Z. So this is this limit of the Stieltjes transform, and maybe let me write here explicitly. So what is the Stieltjes transform? So this is the expectation of the trace of the resolvent of the matrix. And now the matrix is this M, so this is this 1 over n F transpose minus Z times the identity. The identity here in the M by M matrices, and then we take the inverse, minus 1. So this is the trace of this inverse, and then the expectation. That was our Stieltjes transform. And this has a limit if M, all those guys go to infinity in such a way that M divided by N goes to gamma, and P divided by M goes to gamma twiddle. And of course the limit on this equation depends on gamma and gamma twiddle, and of course it should also depend on the non-linearity. Okay, and maybe the interesting thing is that only a bit of information of the non-linearity goes into the equation. So it's namely it's just two parameters, two numbers which I calculate for my non-linearity, which enters the equation. So let me write down the equation. So this Stieltjes transform has a limit. Okay, and this limit S of Z satisfies the following. And now it's an equation of fourth order, so quartic equation. Okay, so it's a long theorem, so I need again more space to continue. So let me write down the equation over there. Okay, so it's of course it's kind of, so it's 1 plus Z times S of Z. And then, okay, and then there are two parameters, theta 1 and theta 2, which are calculated from the non-linearity, and I will write them down later what they are. Those are really the information about the non-linearity, and they show up at various places. So I have here theta 1 times S of Z times 1 minus gamma 1 plus Z times S of Z Okay, so it's a long equation. Okay, so one part minus, then I have a theta 2, a different quantity, divided by gamma twiddle, s of z, 1 plus z times s of z times 1 minus gamma, so the same quantity as here, 1 minus gamma, 1 plus z, s of z, and then still a last one, theta 2 times, and now I have theta 1 minus theta 2 divided by gamma twiddle, and then I have an s of z squared times 1 minus gamma 1 plus z s of z, and this guy here squared. Okay, so it's complicated, and maybe the details are not important for now. I mean, the important point is that I get an equation, and maybe it contains, of course, it contains gamma and gamma twiddle, so the ratio in my matrices, but then it also contains those theta 1 and theta 2, and I mean, they are defined in terms of the non-linearity sigma, so I should also tell you what they are. So the theta 1, and of course this depends on omega. So what is this? So this is the integral of the square of sigma, and again integrated with respect to the Gaussian density. So in the same way as I had here my normalization condition for the sigma, I integrated with respect to Gauss, and all those theta 1 and theta 2 are also integrating with respect to the Gauss distribution, some version of sigma. So here I take the square of sigma and integrate it with e to the minus t squared over 2, okay, dt. Okay, and now the normalization here is somehow important. Okay, and the theta 2, which of course depends also on omega, so there I'm integrating the derivative of my function. So I take the derivative of this sigma, integrating it with respect to the Gauss distribution, dt, and then I take the square of the whole thing. So that's the square of this. Okay, so I mean, this looks at the moment quite arbitrary. I mean, you have no chance of guessing anything like this if you ask about this. So we really, I mean, we should see how we get something like this, and maybe we should also think a little bit about theta 1 and theta 2 and what maybe this here means. And in the new assignment, which should come out today, you are really asked to do some simulations with random matrices like this and check that, I mean, what this equation tells you really is satisfied. Okay, but maybe let us look on a few special situations. So what does this equation tell us? So the goal, I mean, the goal will of course be to maybe to prove this, or at least go in a direction and see how can we prove this theorem. But maybe first we should understand it a little bit better, and for this maybe it's good to look on special cases. I mean, you really should realize that somehow the resulting eigenvalue distribution only relies on very few features of the non-linearity. I mean, we can apply more or less any non-linearity entry-wise, and maybe you would expect that you can really change a lot with the distribution, but actually you don't have so much freedom. So you only get something like this, which is still of a very special form. And maybe let us try to understand a little bit better. So first of all, of course, we can maybe choose special thetas. So let us look on this. So first remark, I mean, in particular, you see if theta 2 is equal to 0, it's getting much simpler. Then the two of the three terms here vanish. So if theta 2 is equal to 0, and let's say theta 1 is equal to 1, then this reduces to what? To just the equation 1 plus z S of z. This is, okay, this is 1, and then I have S of z times 1 minus gamma 1 plus z S of z. So, okay. Yeah, and if you look a little bit closer on this, you will realize that this is actually the equation of our Marchenko-Pastur situation. Okay, I mean, yeah, maybe if you rearrange terms. I mean, there are many different ways of writing the equation for Marchenko-Pastur, but this is really the one which we had when we proved Marchenko-Pastur. So this is the equation for Marchenko-Pastur. I mean, this was what we derived in the proof of the Marchenko-Pastur law, which was 4.2. Okay, yeah, and I mean this is a bit maybe surprising, because what we have here, of course, is we take a product of two. I mean we know Marchenko-Pastur is what we get if I look on X transpose. But now I take the product of an X and a W, and then I apply, if I apply with the right non-linearity entry-wise, I come essentially back to X. So I can change the product back to just having one of the matrices, which is quite surprising, or it's not really maybe clear at all. And so this means, so in this case, actually our M has the same eigenvalue distribution for M transpose. M, let me see, M is, no, maybe M is here not, so maybe I mean F. F behaves in the same way as Z, which means F transpose has the same eigenvalue distribution as Z transpose, where Z is now just an ordinary Marchenko-Pastur. So, because I mean it's like X, but the X was used there, so maybe I use here a different name for this. So Z is a M times N standard Gauss matrix. I mean, that's what this equation is telling us. I mean, this is not clear directly. And I mean, I have to apply a specific kind of non-linearity, entry-wise. Good. Okay, maybe another special situation is if I can get rid of the third term if theta 1 is equal to theta 2. Then this term will disappear, and then it's not fourth order anymore, but then it's only third order. So that's a very special situation. So namely, if theta 1 is equal to theta 2, and let's say theta 1 or theta 2, we also have it equal to 1, then this reduces to a cubic equation. Namely, this is 1 plus z times f of z. This is f of z, so s of z times 1 minus gamma times 1 plus z s of z times so this is taking what is it? What have I taken out here? Okay, so and 1 minus 1 divided by 1 over gamma 1 plus z times s of z. So let me see. Yeah, okay, so this 1 times this is the first term here, and the second, and this times this should be the second one. So theta 2 is equal to 1, and I divide here by gamma twiddle. And so you see it contains now gamma and gamma twiddle. In the first case, the gamma twiddle was also gone. Gamma twiddle didn't play a role there. Okay, so this is now okay. This is something which we don't recognize, but maybe we can see to which situation this corresponds. So this corresponds to a situation of a non-linearity where theta 1 is equal to theta 2, and let's say both are equal to 1. It's very easy to come up with an example of such a non-linearity where this happens. So namely, what do we need? We need that here both guys are equal to 1, and this we can actually achieve if sigma is actually not non-linear, but it's actually linear. So namely, if sigma of t is equal to t. Because I mean, if sigma is the identity, then sigma prime is just 1, and then I'm integrating just over the density of Gauss, which is normalized to be a probability measure. So this integral is 1. So this guy is then 1. And here I have sigma of t is equal to t. So here t squared. I'm calculating the second moment of Gauss. But I mean, this is Gauss with variance 1. So this means the second moment is 1. Okay, so this means this situation where theta 1 is equal to theta 2 is equal to 1 can be achieved by choosing the non-linearity as just the identity function, which means then we are just looking on the product of w and x without a non-trivial sigma. So this means this is actually the situation where I have the product of two Gauss matrices. Okay, so maybe, I need more space. The theorem is so long that it's nothing left. Okay, I think this part of the theorem can go. So theta 1 equal theta 2 equal 1 is given if I'm choosing sigma just as the identity function. Okay, and maybe if I don't want this to be equal to 1, but just equal, then of course I can just multiply sigma with the corresponding theta, or the square root of theta. Because I mean, so if I choose here, let's say the square root of the theta, let's say the theta 2, they are the same. So it's a linear function, a multiple of t. Then of course in the derivative I get the square root of theta. So if I square it, I get theta 2. And here I have the square root of theta 2, and if I square it, I also get this. Okay, so then both theta 1 and theta 2 are theta 2. Good, okay, and so this means, so what I have here is that my f, in this case, for this special situation, corresponds actually to just this product here. And maybe I multiply it then with this square root of theta 2. So this is this is the square root of theta 2, which is just a constant, and then I have w divided by square root of p times x. Okay, so this means I get here a situation. In one case, I get a situation where I really have a product of two Gaussian matrices, but for other choices of the sigma, I get a situation where I just have one Wishart matrix. Okay, and if one looks more on this, I mean, this is now not so clear. Actually, what I get in general for arbitrary theta 1 and theta 2 is essentially a convex combination of these two situations, where I combine independently this with this. So this is in general. So one actually has a kind of independent combination of those two situations. So the f always corresponds 2, a combination, and this combination depends on theta 1 and theta 2. So it's a theta 2 times w divided by square root of p times x plus theta 1 minus theta 2 square root times z. Huh? So I mean, we now looked on a case where where theta 2 is equal to 0, and then we just had this situation here, and here we looked on a situation where theta 1 is equal to theta 2, and we just had this. But in general, if for arbitrary theta 1 and theta 2, we have always a situation like this, where this set here is now a standard Gauss matrix, which is independent of those guys here. But this means, of course, the set behaves in the same way as the x, or in the same way as the w. I mean, each of them is essentially corresponding to a Wishart matrix. Okay, so where w, x, and z are independent standard Gauss matrices of the corresponding sizes. Good. Okay. And so this means, I mean, this is somehow a strange thing. This means that, I mean, in principle, I start from this. So I take this product here, and then I apply a non-linearity to this product. And the effect of this non-linearity is that actually the non-linearity disappears, but I get an additive noise. So I mean, this here is a kind of noise to this problem. So instead of applying a non-linearity to the entries, this has the same effect as adding a Gaussian noise to it. That's what this theorem is saying. Okay, and this is something which at least numerically you are asked to check for specific theta and theta 2s.